And so Adam is a PhD student at Johns Hopkins University in the lab of Sridevi Sarma. And his talk is on neural fragility of intracranial EEG networks towards an EEG fingerprint for the seizure onset zone. So whenever you're ready, Adam.
All right, cool. All right, thanks everyone. And yeah, thanks the moderators and especially Neuromatch for providing this opportunity. So yeah, I'll get right into it. So I'm basically going to talk to you today about drug-resistant epilepsy. And these patients have very poor outcomes right now. Essentially, it boils down to 60 million plus people worldwide are affected by epilepsy. And then 30% of these don't respond to drug treatment. So the only treatment available at that point is surgery. However, only 18% of patients actually opt for treatment, whether it's surgery or stimulation. And that's primarily due to the fact that clinicians only accurately diagnose and treat the patients maybe around 50% of the time. And so this is, after taking essentially like a temporal lobectomy on your brain. And also hospitals lose money on each failure. So in epilepsy, there's this concept of the epileptogenic zone and seizure onset zone. And so epilepsy is characterized by unprovoked seizures. And this EZ, if you will, is defined as the minimum amount of cortex required to be removed to produce a seizure, or minimum amount of cortex required to produce a seizure. And so that definition I just gave you isn't actually rigorous. There's no way that any clinician or human, for that matter, unless you're God, you're able to know what the EZ is. And so really what clinicians strive to do is they try to identify potential seizure onset zones, and then they'll do a surgical excision. And they hope that this actually encompasses the actual EZ. And so the only true labels you ever have access to are the seizure outcomes, as well as the initial clinical diagnosis. And so I'll walk you through a standard clinical hypothesis generation. And so we'll start out with sort of a rough schematic of how epilepsy might be presented. And so in the red, you'll have, say, the ground truth EZ region that we'll never actually know. And the rest of the brain will be normal. And so there will be varying degrees of complexity ranging from a lesional epilepsy, which is something that you can identify on the MRI, to temporal lobe epilepsy, to extratemporal lobe epilepsy, to multifocal epilepsy, where seizures are originating from multiple regions of the brain. And clinicians will typically do ECOG or SEG implantations and look at various snapshots of recordings. And they'll try to visually identify various features of these EEG signals and basically try to localize where the seizure onset zone is occurring. They'll form a hypothesis, and then they'll perform subsequent surgery, and essentially an outcome will be measured based on whether or not they're seizure-free or not. So rather than analyzing EEG signals on a channel-by-channel basis, we take a different approach where we hypothesize that seizures manifest as a byproduct of unbalanced EEG networks. And I'll try to explain more rigorously what we mean there. So on the left-hand side, we have a balanced EEG network where, everything is oscillating, but nothing is straying away from baseline. So you can think of this as if you apply an impulse to a linear system, all its eigenvalues are within the unit disk. And then on the right-hand side, you have an unbalanced EEG network where you see that essentially after a certain period of time, large oscillations and large amplitude EEG signals occur. And we believe that this is due to an unbalanced EEG network where there's potentially imbalance of excitatory and inhibitory connections. And so the observation is that, well, we've seen this happen in rat and histology cells, essentially, where this can manifest due to loss of chandelier cells, where there's decreased damping in the network, or abnormal axonal sprouting of pyramidal cells, which leads to increased excitation in the network. And so we want to model this using computational methods. And so I'll bring you back to this slide where we don't actually have ground truth. We don't have access to the underlying EZ. And so instead, what we do is we take a look at what clinicians do, and we try to perform an analogous approach. So we have spatial temporal intracranial EEG maps, and clinicians use a concordance of various data modalities such as neuroimaging and non-invasive monitoring. And they work with a team to try to perform consensus to determine their confidence in their SOZ hypothesis, and then they perform surgery. So we take spatial temporal feature maps that are split by this hypothesized SOZ that the clinicians label. We construct a structured representation of these two signals over time. And we use an ensemble of decision trees, specific variant of random forest, to compute a probability of success for that seizure outcome. And so in this way, we can compare versus a ground truth label that we actually have, which is the outcome of the surgery. And here, note that if you have a really good feature representation of the underlying epileptic network, then you would think that this approach should provide you with the ability to be able to predict outcome very well. And so we take this approach and we apply a model that's described in the paper known as neural fragility. And I'm happy to answer questions on that at the end. But we basically construct these heat maps that are essentially one-to-one correspondences with the original intracranial EEG. And specifically, we take a sliding window, compute a linear system, or estimate a linear system. Then we estimate how fragile each column is, or each channel of the intracranial EEG network is to within the network. And we specifically compute how much energy it takes to destabilize the network, to basically shift its eigenvalues from within the unit disk to outside the unit disk. And here we present a heat map of an ECOG example, where the red electrodes on the left-hand side correspond to where the clinicians hypothesized as SOZ. Orange represents where they actually did the surgical excision. And on the right-hand side, we have this fragility metric, and the red electrodes correspond to these exact SOZ hypotheses. And then the color represents our fragility metric that we computed. Now, note this metric isn't computed using labels. It's not a machine learning classifier. It's just simply a hypothesis that we generated based on observations of epilepsy data. And if we look at the raw EEG itself, okay, well, we kind of see similar activity. If we, I mean, I'm not an expert EEG reader, so I wouldn't know. And so I'll show you another example. So here's a successful laser ablation where I think the effect is even more pronounced here, where we have a specific ablation at a very small region on this depth implantation. And we see basically very high fragility of these, set of 3 channels. And even in the raw EEG, okay, I think there's some more oscillations, but here I'm kind of cherry picking for you to basically show you the best examples as possible, right? So then if we go to a failed example, what do we see? I think that's really kind of the harder question to ask. And so again, we have where the clinicians predicted or hypothesized as SOZ, and then we have everywhere else. And I think with a failed case, we would hopefully expect to see, as we see here, that there's a high degree of fragility or this feature value outside of where the clinicians annotated. And so this kind of drives us towards trying to quantify this effect across 91 subjects specifically. And so we perform an experiment over our data set that's listed in the paper, where we have 91 subjects and we perform a 10-fold nested cross-validation. And here we're reporting statistics on the test set. Now, granted, we're basically optimizing a classifier for every single feature that's listed on the x-axis here, right? And the x-axis just has a lot of features that are traditionally looked at in the epilepsy community, as well as the neuroscience community for that matter. And then, so we see that in terms of area under the curve and average precision, the neural fragility feature representation generally performs the best. And we can quantify this effect size as well as the statistical p-value. And we also still have the best performance. And so in terms of the p-values, it can be seen on the y-axis that, okay, pretty much everything is quote unquote significant. And I think that's a really good lesson to basically visualize other statistics as well, not just the p-value generally. But this is also good to know that it's an order of magnitude better in that respect. So the next thing we tried to look at was essentially looking at how these predictions are when they are stratified by clinical covariates. And so for the people that are unfamiliar with epilepsy, here on the x-axis on the left is the clinical complexity. So we would expect that these are, you know, from lesional to temporal to extratemporal to multifocal. It's harder and harder. So generally, you're more likely to fail, right? But we didn't optimize specifically on predicting clinical complexity. But we kind of see in terms of the success probability that was predicted that lesional and temporal lobe epilepsy patients will generally have a higher probability of success than these other ones. And so that's good to see. And then on the Engel class and the ILE class, these are just different stratifications of how much seizure was reduced post-surgery, where 6 and 4 are the worst, basically no change at all. And 1 is basically seizure-free, you can imagine. Now, so we optimized in this classification approach of 1 against 2, 3, and 4, but we see the trend from 2 to 4 decreasing as expected. And same with ILAE, where we essentially optimize 1 against the rest, but we still see a relative trend decreasing from 2 to 6, which is really great to see in sense of, you know, matching against what clinicians are already using to label their seizure outcomes.
Hey, Adam, I just want to let you know that it's been a little bit past 12 minutes. So if you could wrap up in the next minute or so, that would be great.
Okay, yeah, sure. All right. Yeah, I have 12 minutes on here. Okay, yeah, just saw it. So, all right, I'm just going to skip to the end. So what did I show you? That the EEG is a manifestation of a fragile network characterized by seizures. And one can compute this notion of fragility from a linear dynamical system network on every channel in a sample of intracranial EEG data. And neurofragility in this classification task that we pose outperforms traditional features. And in future work, we're exploring how it can be used interictally as well as on scalp EEG data. And yeah, I just want to thank funding and collaborators and LabMates and stuff. Yeah, thanks.
Awesome. Really fantastic talk. Thanks, Adam. So Colin has a question. Colin, do you want to just ask it?
Yeah, sure. I mean, one was a quick one. Is this computed on the full bandwidth signal or band limited?
Yeah, so it's band limited in the sense that so intracranial EEG, we generally get, for at least the 91 subjects we have, we basically had usually 1000 hertz sampling. And so I constrained the signal to be between 0.5 and 300 hertz. So it's just like trying to capture everything as well as possible without any DC shifts and as well as nothing crazy high frequency, basically.
I have a quick question on, so this fragility measure, is this, I assume this is sort of like between pairs of electrodes?
Yeah. So we actually have a pretty good example here, I guess. We have a quantitative 2-node example, I guess, if you will, where you can imagine that just for simplicity's sake, we have an E and an excitatory and inhibitory node. And so going from left to right, we have, say, a linear system that's characterized as such. Now note that in our case, we're estimating the A, but here, okay, so we have the A. So say you don't apply this perturbation and estimate how much energy it takes to destabilize the network, then that perturbation norm is 0. And so if you apply an impulse response, it'll kind of be like, it'll act as a quote unquote balanced network, if you will, like the impulse response will decay to 0. Now, if you alter the connections on node I, or channel 1, say with a norm of square root of 5, you'll notice some difference in the impulse response. Now, if you modify just enough such that you shift the eigenvalues past essentially the stabilization point, then say that's square root of I, then you would have a seizure, right? And so this square root of I would be what we call the fragility of node I. And then you can imagine that we repeat this procedure across all channels. Hopefully that answered your question.
Yes, that does. Thank you. All right. Thanks again, Adam. I think we're going to move on now to our last speaker. This is Andrew.